We begin chapter 3 now. So this is the chapter on basic topology of R. Everything that we're going to be discussing now can be extended in a very natural way to higher dimensions. So this is all about what happens in R, so we restrict ourselves to the real line. But all the statements that we make here and the way we construct open sets and stuff like that can be extended in the following way. For instance, we're gonna introduce some neighborhoods of points, and basically, well, neighborhoods of points are points that contain some open balls. I mean, that's the general way of thinking about it. And open balls centered at a certain point are all points that are within a certain distance from the given point. So you have the ball centered at X with radius R. All the points that are within distance R from the point in distance R from X. And so naturally, in the case of R, this is just going to define an interval. So interval X minus R, comma X plus R. So the open ball would be the open interval X minus R, comma X plus R. And the notion of distance everything here will depend on the notion of distance. The notion of distance is not something unique to R. You can talk about distance, and we have already defined distance in general n-dimensional Euclidean space already. I mean, I hope that you've seen that. I mean, you needed it probably for linear algebra anyway. But so this is the thing. So even though we're going to be restricting ourselves to R, everything that we do applies to Rn as well. So the theorems, I mean, everything, of course, that requires an order, so being able to compare two points, saying that something is bigger or, smaller or bigger than something else. And that is very specific to R and cannot be extended to higher dimensions. But most of the things will not require us to do that. Yeah, of course, even when you are in Rn, you still have to compare distances, but that's a whole different thing. Here I'm talking about comparing functions, and function is greater than something at some point. For instance, you cannot, the intermediate value theorem does not apply in the same way, for instance. But other things, can be extended, and the basic topological statements and everything that involves closed open sets and closed and open sets and compact sets and all that. The consequences of compactness, they all apply to higher dimensional spaces. So just to get started, the chapter starts with a discussion on the Cantor set. And the point of the Cantor set, we're gonna skip that. So the only point of the Cantor set is very good. It provides a very good example for many pathological things that people yes, many pathological people things that people at some point in the development of basic topology of Euclidean space ask themselves about. And some for instance, one thing that one property of the Cantor set is this is a perfect set, and we're not going to discuss that now, but yeah. So then that implies immediately that it is uncountable. This is very, the argument to prove that, I haven't even defined what it means for something to be a perfect set, but it's not necessary. The arguments are kind of like the argument for the uncountability of R. In fact, the Cantor set, there's a bijection from the Cantor set to the real numbers. It's a very clear thing to do. So the construction for the Cantor set is just, it's an infinite intersection of closed sets where you remove the middle third. So you have this interval 0, 1. You start by removing this part, then you remove this part and remove this part, and keep going forever. And if you write down what we're doing, if you write numbers base 3 instead of base 10, you're just considering numbers whose expansion base 3 do not contain the number 1, so just 0 and 2. And once you realize that, you can clearly map that bijectively to the real numbers by looking at the expansion. And every time you get a 0, just map it to, and considering the binary expansion of the real numbers, then you can map every 0 and 0 digit, or every term in the expansion, so every coefficient of the expansion. So we have something like, you have an infinite sum of a minus n. Just gonna say n equals 0 to infinity because we're considering numbers from 0 to 1. You can map this to n equals 0 to infinity to an over 2, 2 to the minus n. Since an is either 0 or 2, this is a number, this is 0 or 1. 0 or 1. And it's an exercise for you to prove that, this f here is actually a bijection. But so that tells you something. So there's a very small set sitting inside of the unit interval that is has the same cardinality as this other the interval itself. So the counter set sits inside the interval 0, 1, and it has the same cardinality. It's also a counterexample to other things. For instance, it is a set that is uncountable, but it has measure 0. Measure is something that is not part of this course, but it's a natural thing. If you are to continue doing math, next thing that we may do. One of the topics that we may cover next semester. This is a baby version of measure theory towards the end. But then in later courses, you may need to take a measure theory integration. And this provides an example. So the Cantor set provides an example of a set that its cardinality is very big. It's the same cardinality as R. This measure is 0. So, so there are many other many properties like that that appear over and over in analysis of things things where the Cantor set plays a role. And is a good source for counter examples or for things that clarify why certain statements are true and why some things work and why do you need certain hypotheses. Another thing is to define notion of dimension. There are many notions of dimension out there, but one of the things for the fractal dimensions, the Cantor set, the Cantor-like type type sets that there are like the Cantor set in a certain way. They can be constructed in a similar way. Have a dimension. There's a way of defining associating a dimension to those sets, and those sets are not 0. For instance, you think of points and a finite unit of points as having dimension 0. The real line having or an interval having dimension 1, or line or something like that having dimension 1. A line, even a straight line in higher dimensions has dimension 1. But the counter set is an example of a set for which we can assume, I mean, when you consider this, this definition of fractal dimension, you can associate, you can associate a dimension to the counter set, and it's not neither 0 nor 1, so it's something in between. And so it allows us to discuss things like that, like the fractal dimension, and know that there are some things that are not zero-dimensional or just one-dimensional, but there are some sets that lie somewhere in between. And that's one of, I mean, there are other things, and the counter set plays a role in other things, but this is a very, so this is a very good example of kind of a strange set that will give you, will give you a source of counter examples and things like that. I mean, for courses to come, and yeah. But as I said, this is not very relevant in what we're gonna be talking about next. So I'll just leave it to you to read the rest of that section. The rest of that part, and we'll start with 3.2. Open and closed sets. Remember that we are in R, and so here they define the epsilon neighborhood. We have a point in R, so the points there are, as I said, within distance epsilon from A. Okay, and well, what I said before is that, in fact, the numbers x such the distance or the absolute value of x minus a, the x minus a absolute value is less than epsilon, is simply can written explicitly here as the set of points in this interval, in this open interval. And this is called an epsilon neighborhood. As I said here in R, it's not something that you concern yourself for now. As long as yeah, as long as you understand what's going on for the real line, well, that's all I want. So now, but of course, this is what we care about for now. But as I said, say in 2 dimensions, then you can imagine what happens in more dimensions. But you have a point, say here, in R2, and an open set will be all the points that are within distance epsilon here. So this is epsilon, and this is the point A, which would now be a vector, and A1 and A2, and then there will be the analog of that. So that's the correct way of thinking about it. Not that this is an interval, but there's a set of points that are within a certain distance from point A, the center of that. So this is in R. This is the situation in R. The many things in R may be misleading, so that's why I'm telling you how you should think about these things in higher dimensions. And so now the central thing here is really this definition of epsilon neighborhood. And most of the statements have to do with what happens, with quantifiers involving there exists a neighborhood, so exists something, there is something, or for all epsilon greater than 0. Typically, if those statements are going to fail for some small epsilon. So we typically, that's why we use the notation epsilon. In principle, when you say something is for all epsilon, say something holds for all epsilon, of course it needs to hold for big epsilon, but it's much easier for many of these statements, it's much easier to be true when epsilon is big. So everything is gonna be decided when epsilon is small. So the same thing happens when we were considering sequences and series, so where the tail is actually the thing that we need to be concerned with. I mean, this is what contains all the information about convergence or anything, or everything that we care about for that matter, when we're studying sequences and series. Something similar happens here. And so everything here that just depends on what happens for the small values of epsilon. So now the definition, and this is what is the crucial thing. So we're going to define an open set now. A set O subset of R is open if for all A in A there exists epsilon greater than 0 such that the epsilon neighborhood of A, is completely contained in this open set. You should not think, so this is a bit of a warning, you should not think of open sets as just being open intervals. But of course, this is the kind of structure we want to preserve. For instance, if you consider an open interval, so say 0, 1, 0, 1, so the open interval 0, 1, no matter, so if a point belongs here, it belongs to the interval 0, 1, to the open interval 0, 1, no matter how small, how close to 0 or 1 that point is, so it could be very close to 0, you can always find a number that is smaller than x and bigger than 0. So that should not be a mystery, because that's the Archimedean property again. And once you realize that, you can plug in an epsilon neighborhood here, a very small, you do blow this thing up, you'll see that you can find a small epsilon neighborhood of x, right? So this is going to be the epsilon of x, right, or A. Maybe we should use A since this is the notation for, meaning the definition. Okay, so this is true, but the thing is, we're not allowing A to be either 0, neither 0 nor 1. But if instead we consider the closed interval, so if instead we consider the closed interval 0, 1, you see that no matter how small the epsilon is, so if you're sitting at 1, say, you're gonna be so this is a v epsilon of 1 for epsilon really small. So this whole interval here is this interval here is the v epsilon of 1. No matter how small it is, you're always gonna you're always gonna contain elements that lie outside of the interval because that's exactly like at the border, if you will. And so you're gonna pick up some things that are on the other side. So when if you include the points like this, like the endpoints inside an interval, I mean endpoints of an interval, then your set is not gonna be an open set because you're not gonna be able to fit a full epsilon neighborhood. If you pick up the endpoint, you're never gonna be able to fit a whole epsilon neighborhood inside the interval if you pick up an endpoint. And that's the point of, yeah, including the endpoint, so that when you pick it up, I mean, you can choose that as the center of your epsilon neighborhood and then violate this condition for this definition to hold. So, epsilon neighborhoods, this is how they play a role. So open sets are sets such that for all points inside, every point inside can be put inside an epsilon neighborhood that is completely contained within the set. So that's an open set.